Tate from the Spaceguard Centre, which is a working observatory which tracks near-Earth objects, comets and asteroids, which could hit the Earth. He's based in rural Wales, so we're hoping his connection tonight will hold up. It's been doing well earlier on when we were chatting with him. But Jay is a very interesting character. He has given a talk before. We think it was about 10 years ago. So lots has happened in that time. He's a former British Army major who helped NASA track potential doomsday space rocks. In 2013, he was awarded the Europlanet Prize for public engagement in planetary science. And in recognition of his work, asteroid 15117 has been named J. Tate in his honour. So he's actually got a little world named after him. He's been all over the British media, from Channel 4's Big Breakfast to BBC's Newsnight. So we're delighted to have him give our talk this evening, all about his very own Spaceguard Centre. Over to you, Jay.
Thank you very much indeed. I'll just try and share my screen, which is always slightly dodgy. Right.
Well, I can
have a picture. Do you have a picture?
Yeah, and it's just gone full screen. It looks great.
Ah, righty-ho, jolly good. Well, first thing to say is thank you very much for inviting me along this evening. I seem to remember the last time I came was actually on your territory, and a fairly hairy weekend, I have to say. But on to this evening's business. The work we do here is involving the near-Earth object hazard, the likelihood of asteroids and comets hitting the planet with consequences that could be really quite unpleasant. I have to say, though, that it's a fairly new subject, and by new, I'm really talking about a quarter of a century, 25, 30 years perhaps. And that's due to a mistake that we made, which of course in science is pretty common. In fact, a lot of science is actually dependent on people making mistakes. But this one actually dates back to Isaac Newton. Back in 1687, Newton told us that the solar system was rather like a great big machine. It's mechanical, predictable, peaceful. Nothing ever happens. In fact, it's just like God made it. But a century and a half later, along came people like Hutton, Lyell, Darwin, who told us that actually things do change, but only very gradually over hundreds of thousands or millions of years. Really, all of that finished off the old idea of sudden catastrophic change. In the dim and distant past, people knew jolly well that every now and again something big and bad comes along and changes everything. But that idea was really left to the superstitious and ignorant. Until a gentleman called Gene Shoemaker came along in the early 1960s, and he proved quite conclusively that the hole in the ground in Arizona, Meteor Crater, was an impact crater caused by an iron asteroid hitting the Earth. Not a lot changed, but then of course we went into space and we had a close look at the other planets. And that's when the light really went on. For example, this is the surface of Mercury, covered in holes. If you go out to Venus, that one's covered in holes. And if you go the other way out to Mars, same detail. But of course, once you get beyond Mars, the planets aren't solid, just big gas giants. And you wouldn't expect craters on a big ball of gas. But this is what Jupiter looked like back in July 1994, just after it was hit by a whole series of comet fragments. In fact, the dark scars were visible through relatively small telescopes. Everybody could see them. But when that happened, everybody thought it was a once-in-a-lifetime chance to see something actually hitting a planet. And it was. Until the summer of 2019, when it happened again. Nice big flash on the left-hand side of the planet there. It only lasted a couple of seconds, but the fireball was about the size of France. In fact, since then, we've seen half a dozen of these. The latest one was a year ago tomorrow. But if you look at the moons of the gas giants, and the moons, of course, are solid, then we're back to square one. This is Callisto, one of Jupiter's 79 moons, covered in holes. If you go out to Saturn, you'll find a nice little moon called Mimas. Now, the thing that made the big crater was almost big enough to smash the moon to bits. Didn't quite make it in this case. But if you go out to Uranus and look at Miranda, that one was smashed to bits. Later on, because of the gravity between the fragments, they all clump back together again. And there's enough mass to pull it all back into a sphere. But even out as far as Neptune, you'll still find moons that are covered in holes. And just for the sake of those of you who aren't living in the 21st century, Pluto, of course, has the same, covered in craters. So everywhere you look in the solar system, everything's been battered to death, with one big exception. And people used to think that for some reason, the Earth had just got away with it, until we started looking at the Earth from the outside. And that's when we realized we got that one wrong. In fact, as we now know, of course, the Earth is covered with impact craters. But when people started finding lots of these, it seemed to come as a great big surprise. And why anybody was surprised, I'm simply not sure, because all you've got to do is look at the next door neighbor. We share the same bit of space with the moon. So clearly the hit rate there must be a pretty good indication of the hit rate here. We've got a team in the United States who watch the moon just to see if they can see anything hitting it. Since they started back in 2005, they've seen quite a lot. So things do hit planets. There's really no doubt about that. It's just that when they hit, if they're big enough, everything on that planet changes very, very quickly. So we seem to have a little bit of a problem. Things hit planets and we live on one. And that really leaves us with a number of fairly important questions. The first is, what's doing the damage and why? And the simple way of answering that one is to have a quick look at where all this stuff came from in the first place. How do you make planets? And as you know, that one actually turns out to be fairly simple. When the sun first accreted out of the cloud of dust and gas, it was surrounded by a disk of material, gas, dust, ice, and so on, which later accreted into the planetary system that we know and love so well. But that accretion process didn't work in all areas of the solar system. For example, between the orbits of Jupiter and Mars, we have essentially a belt or a ring of debris surrounding the sun which is in fact a planet that never happened. The accretion process was stopped essentially by the gravitational influences of Jupiter. So between Jupiter and Mars, we've got millions and millions of big lumps of rock and metal. We call them asteroids. So the asteroids are really just bits of a planet that didn't happen. The other area where things didn't go quite as planned, if you like, was I thought I'd throw this one in because it has an Irish connection. This is the daily plot of the asteroids from the Armagh Observatory. Now, as I mentioned, the other bit of concern to the likes of myself is a little bit further out. Once you get out beyond the orbit of Neptune, then that disk around the sun, the circumstellar disk, was literally too thin to make planets. So out beyond Neptune, we've got millions and millions of big lumps of ice and dirt, just like big dirty snowballs. And of course, that's the standard model for a comet. So out beyond Neptune, we've got millions and millions of comets, really the leftovers from that original accretion disk. Most people, of course, seem to think that comets actually look something like that, big fluffy things, long tails and so on. And of course, sadly, that's much more what a comet actually looks like. It's a big, dirty snowball. But if one of these big, dirty snowballs does begin to move towards the sun, it'll warm up. And when you warm up ice, it changes. What it can't do, certainly if it's water ice, is melt, because you can only have liquid water if it's under pressure, and space is a vacuum. So the ice sublimes. It literally turns straight from solid to gas. When that happens, then you'll get jetting from the surface of the comet, and that material either falls back down and helps to thicken up the skin of the comet, or it contributes to an enormous cloud right round the whole thing called the coma. But when all of that gets even closer to the sun, then the solar wind begins to blow that cloud away, forming the tail. So the comet's tail is being blown away by the sun, so it always points directly away from the sun. It's got nothing to do with the direction the comet's moving in. But that tail does show that comets are unbelievably grubby things. These are really the solar system's equivalent to the teenager. Wherever they go, they're leaving a trail of dirt and debris. And every now and again, as the Earth whistles around the sun, we go through one of those trails. And that's when you get a meteor shower. So your average shooting star is just a tiny piece of comet burning up in the upper atmosphere, normally about the size of a grain of sand, burning up 15, maybe 20 kilometers above the ground. And in fact, the Earth picks up a great deal of stuff from space. We're doing it all the time. Probably somewhere between 100 and 150 tons every single day. Mainly dust, of course. But every now and again, we get something slightly bigger, grain of sand size, grain of rice size, and that's when we get our meteors. But if we up the game a little bit further to something about, well, say a few tens of meters across, small house up to reasonable size mansion, that's not going to hit the ground. What it will do is it'll pop in the atmosphere before it hits the ground, airburst. Now, back on the 30th of June, 1908, a little lump of asteroid or comet, nobody's quite sure which yet, probably about half the size of a football pitch, came whistling in over eastern Russia. Just over the Tungus region in Siberia, when it was still 5 miles above the ground, it popped. It was about 1,000 times more powerful than the atomic bomb that was dropped on Hiroshima. The heat and the blast completely shredded the forest underneath, just over 800 square miles completely destroyed. About the same area as the Snowdonia National Park. My apologies, I'm Welsh. But just over 100 years after that, in February 2013, everybody was expecting a close approach by a reasonably sized asteroid called 2012 DA14. Close approach due at about 7 in the evening, but early in the morning, the phones began to ring, and it was a number of media and press asking, tell us all about this asteroid, to which the answer was, yep, fine, but you do know it's not happening until 7 o'clock this evening, to which the response was, no, 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 not that one, the one that's just exploded over Russia. This, of course, was the famous Chelyabinsk event back in 2013. It was really small, only about 17 meters across, and it popped about 30 kilometers above the ground. The yield here, probably somewhere between 20 and 50 times the Hiroshima bomb. Luckily, it was far enough away from the city for there to be very little structural damage. The main problem here, though, was glass. What people forgot is that if you see the flash of an explosion, it's not going to be long before the bang shows up, the shockwave. In this case, the flash to bang time was about 122 seconds. Plenty of time for people to realize something was up, go to the window to have a look, just in time for the windows to be blown in. So most of the 1,600 casualties here were caused by flying glass. That one made the press. Of course, these things really aren't that uncommon. Pretty rare to happen near a city or a populated area. But recently, the Americans have published their data on these airburst events. They've been picking them up for decades. But if we up the game a little bit further to a bit of asteroid or comet about 150 meters across, football stadium size, that will hit the ground. And it'll hit the ground at about the same speed as it had been traveling through space. Now, when a thing like that hits the ground, it's not going to stop. It's going to keep on going until the ground physically stops it. But when the ground stops it, the comet or asteroid blows itself to gas. So what you get is a nice big explosion just under the ground, which blows a big hole in the ground. And it's that hole that you see as the crater. And of course, that's why nearly all meteorite craters are perfect circles. But luckily, events like this are fairly rare. But when they happen, it's going to be quite a bad day. For example, if we had that 50-meter sized object, rather like the Tunguska, it's going to take out the area of at least a large city. If we go up to that 150-meter size that actually hits the ground, the immediate effects of that are going to take out a small country, Belgium, Holland, something along those lines. If we go up a little bit further to something about 1 kilometer across, 2/3 of a mile, then the effects of that will, within a few hours, be global. And if we go up to 5-kilometer size, well, then we're beginning to look at the mass extinctions. The famous one there, of course, the KT boundary event 66 million years ago was 10 kilometers across, but it took out 70, maybe 75% of all the species of plant and animal on the planet. We know it happens. We have the evidence, and science is evidence-based. The next question, though, is how often? And by far the best way to find that out is to find out how often it's happened before. And we can do that. We know how to identify craters. We know how to date them. So really, all we've got to do is count them. Somewhere where there's no atmosphere to get in the way, no water, no weathering, but still fairly close. And this one doesn't take the brain of an archbishop to work out, but of course, the next door neighbor, the moon. And it's the crater counts on the moon that have allowed us to put together a fairly robust frequency table that tells us how often we get hit by different sizes of object. For example, if we look at the big fellas, the mass extinction events, we're looking at timescales of tens, even hundreds of millions of years. Not something to keep you awake at night. But if we go down to the ones that have global consequences, we could be looking at a few tens of thousands of years. And on the timescale of a normal civilization, that's pretty significant. Go down to the ones that just take out a large city, then we're looking in terms of years or decades. The point is that this natural hazard is very different to the others that we regularly deal with, earthquakes, volcanoes, tsunamis, and things like that. With this one, it's very, very rare, thankfully. That's a good thing. Or is it? Nobody's ever seen this happen on the news, so it doesn't exist. Bit of an issue. When it happens, though, there is no upper limit onto the amount of damage that these things can do. With the normal natural hazard, there's at least a theoretical upper limit of the amount of energy that can be released into the environment. With the near-Earth object hazard, there is no upper limit. But this one is avoidable. There's not a whole lot you can do about volcanoes, earthquakes, that sort of thing. But the near-Earth object hazard is totally avoidable. Now, making the problem go away, well, it's really a three-step process. The first step is to find any potentially dangerous objects as long as possible before they actually become a problem. Now, back in the late 1990s, NASA was tasked by Congress to find 90% of the big, potentially dangerous asteroids. To do that, they put together a team of telescopes to conduct the search, mostly, of course, in the United States. But they achieved that goal of finding 90% of the big ones within just over a decade. So Congress told them to drop the size, go down to 140 meters. And that's what we're working on at the moment. To do that, a new generation of telescopes joined the game. For example, this is the linear program in Socorro, New Mexico. We've got Spacewatch on the top of Pitt Peak in southern Arizona, the Catalina Sky Survey just outside Tucson. But the real king of the game at the moment is Pan-STARRS. It's a joint United States Air Force University of Hawaii program using 2 telescopes on Haleakala on Maui in Hawaii. We've traditionally had a big gap in these surveys in the southern hemisphere. So to help out with that, the United States Air Force have moved their big space surveillance telescope from New Mexico to the west coast of Australia. And in recent years, there's been a lot more international interest in the near-Earth object hazard. Perhaps the most significant organization to join in is the European Space Agency with their Space Situational Awareness Program. They brought to the table a number of really useful search telescopes and a mass of expertise in planetary science and in space missions to small solar system objects. But in the detection game, the real game changer is going to be this one. Now, this telescope's not finished yet. It should be finished by the end of October in 2024. And I'm sure a lot of you will recognize what used to be called the LSST, the Large Synoptic Survey Telescope, now known as the Vera Rubin Observatory. It's a big one, absolutely no doubt about that. The primary mirror on this telescope is 8.4 meters across. In fact, that's the mirror before they started to polish it. This is not good for those of us with aperture fever. But we have a little bit of a problem, not with the big asteroids and comets. We can find those if we wanted to. It's the little ones, the small objects, a few meters, maybe tens of meters across, that we only pick up when they're really, really close. These are the things that cause these airburst events like Chelyabinsk or Tunguska. To help find those, the United States have developed their ATLAS program. So far, there are 4 of these systems dotted around the world, and they're specifically designed to find small, fast movers. We're not going to get a lot of notice, possibly just a matter of hours. But for an airburst, that could well save thousands of lives. The Europeans are moving along similar lines with the Fly-Eye telescope system, the first of which is already up and running in Sicily. There will be 3 more, but obviously the whole program has been slightly delayed by the dreaded lurgy. But we also have a space telescope, the Wide Field Infrared Survey Explorer, or WISE. It was originally launched to map the entire sky in the infrared. Well, it did that. And when it was finished, it was handed over to the Near Earth Object Project. And it's absolutely ideal. Mainly because asteroids and comets are pretty dark in color. They're hard to see optically. But where they shine is in the infrared. They've been warmed up by the sun. Warm object against a dead, dark, cold background, dead easy to see. Unfortunately, WISE, or NEO-WISE, as it's now known, is beginning to show its age. So hopefully in 2026, it'll be replaced by the Near Earth Object Surveyor, another infrared space telescope, but this time specifically designed to look for asteroids. So we have the technology, both space-based and ground-based, to find these things. But when you find one, you need to know what it's made of, how it's put together, and so on and so forth. And in recent years, there's been a flurry of space missions to asteroids and comets to find out precisely what they're made of. Are they flying rubble piles? Are they solid? Da-da-la. And these missions are providing all the information that we need. They've even brought bits back. You'll be aware of the Hayabusa and Hayabusa 2 missions from Japan. Hayabusa has already delivered its payload back and it's being analyzed right now. The Americans had their OSIRIS-REx mission. That is on its way home right now, bringing back samples. So we can find them and we can work out their physical properties. The next problem, though, is when you find an asteroid or a comet, you need to know where it's going. So you have to track it for a period of time. And these days, nearly all of that tracking is done by amateur astronomers, which actually is absolutely fine. The amateurs provide the most amazing amount of data that's so essential to the whole program. But when we find one that's coming, well, we have a number of options. The first option is to do nothing at all. Just sit back and hope it all goes away, which of course it won't. So probably not a terribly bright idea. We only bother showing it really because for the last 25 years, that's been British government policy. The second option, on the other hand, is to go for the sort of Bruce Willis approach. Let's try and blow the thing to bits. Well, that's absolutely fine. It really just depends how stupid you want to look afterwards, because all you've done is turned a predictable bullet into an unpredictable shotgun blast. The third option is simply to turn a direct hit into a near miss. Give the asteroid or comet a tiny little nudge, just enough to guarantee that it misses. Now, quite how you do that, of course, depends on a huge number of different things. What's your target made of? How's it put together? How fast is it spinning? How much time have you got? And so on. So there's no silver bullet here. What you need is a folder full of different deflection methods to take on different types of target. And right now, NASA is working on precisely that, along with the European NEO SHIELD project. They're looking at things like kinetic energy. You literally smash something straight into it to push it, of course. In fact, as most of you know, at the end of this month, NASA will be doing precisely that with its DART mission. It's going to hit a very small asteroid, and we can then measure how far it was shifted. You might decide to use a process called ablation. Now, the idea here is that you heat up one particular spot on the asteroid or comet, it'll vaporize, the vapor jets outwards, and that acts like a little rocket motor producing thrust in the opposite direction. A slightly cruder way of doing that is the nuclear option. You pop your device some distance away from the object, and it's the heat and the radiation that ablate the surface. But perhaps the most elegant way, if you've got the time, is to use gravity. Park a spacecraft next to the asteroid or comet and edge the spacecraft away. The mutual gravity between the two will tug the asteroid or comet in the same direction. The point is, we can find them, we can track them, and we can make them go away. It's not a case that we can't do it. It's purely a case that we can't be bothered right now. But having said that, we now have an international organization to coordinate all of the national efforts. The United Nations has set up an organization within the Committee for the Peaceful Uses of Outer Space to coordinate all the national programs. A little glint of hope on the horizon. But there's a couple of elephants in the room. Firstly, we can estimate the impact rate on the Earth by counting craters on the moon and observing the number of near-Earth asteroids that we find. However, what we don't have is any firm geological record of airburst events like Tunguska or Chelyabinsk that leave no craters. We simply don't know how often this sort of thing happens. The other problem is the question of whether impact rates are steady, or do these things come in clusters, in bunches? Now, until recently, we've always assumed that the rate has been fairly constant, but the crater record on the Earth seems to show that impacts actually happen in bunches, not at a constant rate. That's difficult to come to terms with, because we've always assumed that the current near-Earth asteroid population is fairly steady, maintained by leakage of objects from the main asteroid belt. But it takes tens of millions of years for an asteroid to drift from that belt into a dangerous orbit. So we would expect the population of near-Earth asteroids not to change much over that sort of period of time. But the evidence suggests that it does. And one explanation for this can be found in things called centaurs. These are comets from beyond Neptune that reach the inner solar system, basically having been bounced around by the gravity of the giant planets, the gas giants. In fact, it's been estimated we've got about 44,000 centaurs in the solar system that are bigger than a kilometre across. They behave both like asteroids and comets. They look like asteroids, but occasionally they show cometary activity like outgassing and so on. They're perturbed from the Kuiper belt and they become Neptune crossing. As soon as that happens, their orbits become chaotic, changing quite rapidly as they make close approaches to one or more of the outer planets. And some of these will move into Jupiter crossing orbits. Now, from there, they can be deflected into the inner solar system. This is actually happening at the moment with an asteroid. Well, it's called asteroid 2019 LD2, actually now classified as a comet. But a centaur will either collide with the sun or a planet, or be thrown out into interstellar space. But as we all know, comets are very fragile things, and they have a habit of breaking up when heated by the sun or put under stress, gravitational or otherwise. We know comets can disintegrate. We've seen it happen. But the disintegration of a large comet in the inner solar system would produce a huge mass of dust and bigger fragments that could pose a threat to the inner planets for certainly a few tens of thousands of years. And that recurring would be episodic. We can also look at the amount of dust currently in the inner solar system, and there's a lot more than we would expect. This suggests that a large comet, possibly up to 100 kilometers across, disintegrated in the inner solar system within the last few tens of thousands of years. But the effects of running through the debris trail left behind by a disintegrating comet can involve the dumping of literally millions of tons of fine dust into the upper atmosphere and the arrival of hundreds, maybe thousands of Tunguska-sized objects over the space of a few hours, days, possibly weeks. These would ignite brush fires globally. They would cause significant damage. Larger objects would cause damage just by sheer kinetic energy. But a lot of detailed modeling on the climatic effects of dust, smoke, and so on in the atmosphere was done back in the days of the Cold War in the context of global nuclear exchange. Dusting in the atmosphere, for example, would reduce the level of sunlight to perhaps that of reasonably bright moonlight. That would result in cooling, which some of you might think might be a good idea, but it would be, in some cases, sufficient to destroy most agriculture, and that, of course, would then lead to societal collapse. So the breakup of a large comet in the inner solar system could generate a large population of small but still significant impactors. It's beginning to look as though we've got something quite badly wrong with our estimates of the number of small objects, a few tens of meters in diameter in the inner solar system. Recent studies from meteor and fireball counts indicate that that number of impactors of that size, a few tens of meters, may be up to 10 times higher than previous estimates based on telescopic surveys and crater counts on the moon. It therefore seems like such events could happen at least 100 times more often than the big Hollywood-style, globally threatening asteroid impacts. And there's an increasing body of evidence that indicates that this sort of thing has happened on a number of occasions already within the historical record. So the Centaur issue is something that, frankly, is going to need quite a lot of close research and inspection. But where does the Spaceguard Centre fit into all of this? Well, we have a number of instruments up here that allow us to do the work that we do. At the moment, the prime, well, not the prime, but the biggest instrument we have is a long focal length 13-inch apochromatic triplet refractor. Not, I have to say, a great deal of use when it comes to the detection and the tracking of asteroids. The field of view on this instrument is simply too small. For the tracking, we use a Schmidt Cassegrain 14-inch, nice, reasonable size field of view for the tracking. But as I say, it's this field of view issue that's a bit tricky. For example, that's a picture of the moon. The 13-inch refractor has a field of view the size of that red rectangle. The 14-inch has a much wider field, and that is actually pretty good for the tracking process. But it's still way, way too small for a search program. For a search program, you want to see a great big wedge of sky. So if we want a search program up here, we're going to need a telescope with a much wider field of view. rather like that one. That's a 24-inch Schmidt camera. Not technically a telescope because there's nowhere to look through it. It's purely photographic. But with a single photograph through that, you can fit 10 full moons across the frame, full 5-degree field of view. Now, that particular camera was in Cambridge at the Institute of Astronomy, but for the last 35 or 40 years, they've not been able to use it properly because of light pollution. So, at the back end of 2008, Lord Rees, the Astronomer Royal, stopped by and asked if we'd like that camera up here as a search instrument, which was jolly nice of him. Problem, of course, at the time, we had no plan, we had nowhere to put it, and we certainly had no funding. But we thought we'd give it a go. It's a beautiful instrument, built by Grubb Parsons back in the late 1940s, when, dare I say, things were built properly. So we went up to Cambridge to have a look at this thing. That's what you've got above the floor in the dome. But as well as that, you've got this lot below the floor. So even when the tube's horizontal, it's over 15 feet high and weighs just over 7.5 tons. And to get it out of Cambridge, it's all got to come out through that little slit in the dome. The dome itself was built in 1910, cast iron frame, zinc plates, and it's a grade 2 listed building. So we can't touch that at all. We had a good look at the instrument. Mechanically, it's absolutely spot on. As I say, built by Grubb Parsons when they did stuff properly, this was built to last. And the mechanical side of things, it's a joy to look at. The electrics, on the other hand, are completely useless and almost certainly lethal. But the most important thing is that the optics are all in fine condition. The primary mirror, 24-inch mirror, does need to be stripped and resilvered, but as you know, you have to do that sort of thing every decade or so anyway. So we removed the major optical assemblies for safekeeping, and then we took a group of volunteers from around here up to Cambridge to give us a hand getting the whole thing ready to move. The first job was to disconnect the optical tube from the mounting, the fork mount, and get that out. And that, I have to say, turned out to be a lot simpler than we thought. She actually popped out quite easily. The real problem, though, was the base and the fork. Partly because that's 6 of the 7.5 tons, but also the right ascension ring at the bottom of the fork is about 13 inches wider than the gap in the dome. So a little bit of toing and froing required there, but she came out nice and clean. And all we had to do then was load the whole thing onto a flatbed and then make tracks for Wales, where, of course, we had nowhere to put it. But one of the volunteers owns an engineering company down in the valley, just down the hill from here, and he had some space in his factory. So we could put the whole thing into his factory, give it a quick once over, and then prepare it for long-term care and prayers. Gave it a good clean, wrapped it up, and then shrink wrapped the whole thing. Remember, at this stage, we still had absolutely zero funding. We didn't have anywhere to put it either. But luckily, one of the other volunteers in the group is an architect. So he was able to put together the drawings and the plans for the new dome. And by the time that had all been approved by the local planning authorities and everything, we'd managed to save up enough for the initial tranche of building materials. What we couldn't afford were the builders, so we thought we'd better have a crack at that one ourselves. So we started building, including things like the concrete plinth that the camera sits on. That's actually a completely separate building. It has its own foundations down to bedrock, and it's isolated from the rest of the building, so there are no vibration issues. In fact, we put the base assembly onto its plinth fairly early in the game to finish off the upstairs floor joists. But then we began to think about the dome on the top. Now, you can buy a 26-foot observatory dome. It's going to cost you upwards of £150,000, so we thought we'd better have a crack at that one ourselves. So we all learned how to do fiberglassing, and within a fairly short time, we'd put together 26 fiberglass dome sections. Each of those, of course, then had to be trimmed, sanded, primed, top coated, and when all of that was done, it was time to put the whole thing together. The plan was to crack that in a single weekend, and that would have worked absolutely perfectly had it not been for the fact that when we were about 2/3 of the way round, it began to pour with rain. Now, it's not a problem for us, obviously, we live in Wales, but it's a real problem for the sealant that goes between the sections. So we had to stop. What we didn't know was that on the following Monday night, there was a very short but very sharp storm, which effectively crashed the whole thing. Until you remember, it's fiberglass, and you can fix fiberglass. So the following weekend, everybody came back up again, and by end of play on the Sunday, we had ourselves a dome. Loads of cracks, tears, splits, but over the next couple of weeks, they were all fixed from the inside. But once the dome was secure, then we could lift the optical tube onto its mounting in the building, and about 15 minutes after that, we lifted the dome. But since then, there's obviously been a colossal amount of work, both on the building and on the camera, not helped, I have to say, by nearly 18 months of absolutely nothing. But we're well back into the swing of things now, working, as I say, on the camera and on the dome. For example, those are the new electrics. They're now all up and running. The drive systems, that's the declination drive and gearbox. This is the main right ascension drive. They've both been completely stripped, rebuilt, rewired. We made a conscious decision to use the original machinery rather than trying to develop new systems, partly because the new stuff would be wildly expensive and complicated, but mainly because the old stuff works brilliantly, and it's part of our scientific heritage. The dome is now motorized, so it rotates under power. Eventually, it'll be slaved to the optical tube. So wherever the camera's pointing, the shutter in the dome will be directly in front of the camera. This has involved the writing of new software to control the dome. We now have an ASCOM driver for our own dome, and hopefully within the next few weeks, we'll be installing that system to see if it actually does what it says on the tin. The shutter has been a bit of an issue, but those issues are now being resolved. So we should have a fully operational dome within the next month or two. We are moving on to slightly more cosmetic things, laying carpet tiles on the floors and things like that. But that doesn't mean that there isn't still a huge amount of work to be done on the instruments, the camera itself. For example, this is the mechanism at the front of the tube that allows you to adjust the Schmidt corrector plate. Quite a simple process, but a mechanism that's insanely complicated. On the same sort of tack, this is the mirror cell. Again, insanely complicated. However, it's been completely stripped, cleaned up, parts replaced, rebuilt. It will work in exactly the way that it was designed to. The mirror itself, as I mentioned, needs to be stripped and resilvered. In fact, as we speak, that mirror is sat in an acid bath at the Optical Engineers over in Essex, which is stripping off all of the old coatings down to the glass. Once we're down to glass, it can have a proper optical inspection and then straight into the vacuum chamber, 3 microns of aluminium and a silicon oxide protective coat. Then we can drive 150 miles to go and fetch it. It's worth pointing out, probably this is a non-trivial piece of glass, 24 inches across, 4 inches deep, weighs in at about 160 pounds. But the other thing we've had to consider is the actual imaging system. Now, the original was designed to use the cutting edge technology of the early 1950s, which was a 6-inch glass photographic plate. In fact, this is the original plate holder with a 6-inch glass photographic plate. Now, of course, in this day and age, that is simply not going to happen. So we're replacing all of that with a rather nice research grade CCD camera. In fact, in recent weeks, about a month ago, in fact, we decided to try out the mounting that we built for the camera in the tube. And I have to say, it's still there. If it ain't broke, don't fix it. So a little bit of cable management, but once that's done, essentially the CCD camera is installed. What we won't get, of course, is that full 5-degree or 10 full moon field of view. If you wanted a CCD chip 6 inches across and curved, then you're talking 7 figures. But we'll certainly get at least 2 degrees by 1.5, which actually makes this an extremely capable search system. But to make it all happen, we launched the project. It's called DRAX. All projects here at the Spaceguard Centre are named after James Bond villains. Can't possibly do acronyms, they curl the toes. But the aim of this is to get the wherewithal to bring the camera back into service and to build the dome. Since we're not funded here in any shape, manner or form, it's all down to people putting pennies in a box in our little shop. In fact, the entire project budget would just about get you one of those. The project's also caused quite a lot of interest in the press and the media and so on. In fact, during lockdown, the new dome was taken over as a TV studio for a Channel 4 programme. And I have to say, what's been really nice is the amount of support for the project that we've had from some fairly key people in the near Earth object and other games. Always good to flash up photographs of famous people. But I go back to earlier on in my talk, the near Earth object impact hazard is probably one of the most crucial that our species faces. In fact, it's the only natural hazard that we know of that could render our species extinct within a matter of weeks. But, as I mentioned earlier, it is a problem that's very, very rare. Good thing. But when it happens, there's no upper limit on the amount of damage to the environment that can be caused. But unlike other natural hazards that we're used to, this one is avoidable. We can make it go away. It's not a case of we can't do it. Right now, it's a case of we can't be bothered to do it. So I leave you with one very, very simple question. Are we any smarter than the dinosaurs? And at that point, I think I'd better pause.
Thank you.
Hello?
Thank you, Jay. Sorry about that. The feedback there. That was an excellent presentation. Especially as a telescope person, I could ask you lots of questions about the actual instrument. But
well,
we'll invite people.
Absolutely fine.
Yeah, we'll invite people to post their questions in the chat or just turn on their microphone. And while they're thinking about that, I might just ask you, the clear aperture of the telescope, is that 20-inch at the front? The camera, Schmidt camera, I should say.
Yep, you've got a 24-inch primary mirror and a 16-inch corrector plate.
Right. And what F ratio does it work at?
It currently is working at 3.4.
No. And I saw Andor there, the camera, a good Irish/Belfast company.
Absolutely, yeah.
Are they sponsoring you, or do you have to pay the full price? I know those cameras aren't cheap.
They're certainly not cheap, and that's why a 90% discount was taken with open arms.
Wow, very good. I'll talk to you about that.
Well, they provide cameras for the LCOGT telescopes and Forks and the Liverpool telescope. So we were able to tap Andy Newton up at Liverpool John Moores to have a word in the ear, and they had a fully reconditioned demo model at 90% discount.
Wow. And what spec is it in terms of pixels by pixels?
Well, the great thing about the camera is that it has very large pixels, which is exactly what we want. We're not taking pretty pictures. We want lots and lots of photons on the pixel. So it's 2048 by 2048. Pixel size, if I remember, is a 13.5 micron.
Great. Well, let's see if any.
Hello?
Sorry, guys. I think David's having some issues with his audio.
Oh, no problem.
All good. Until we get him back, has anyone got a question for Jay? So we have one here. Can you see that, Jay, or would you like me to read it out for you?
Oh, yeah, I can. Sorry, it's a little box I'm not used to seeing.
I'm new too, no worries.
Which has now disappeared. So.
Okay, I can read it out for you. Hi, Jay. You mentioned that there are over 2,000 impacts on the moon since 2005. Are these tracked visually?
I don't think I mentioned that there were 2,000 impacts on the moon, just an awful lot of them. They're picked up optically by the flash that they make when they hit the surface. So we're looking at small but significant objects. And right now, I can't remember how many have been picked up, but it's a fairly constant flux. But it's purely optical, purely optical.
Interesting. I have another one here for you as well. So I think the Angelus was instigated by the Pope in the 10th or 11th century to protect the Earth from comet impact. There was a lot of cometary activity at that time. What do you think about that?
Well, the historical background to all of this, certainly with the Centaur issue, is ongoing right now. I mean, it's new. Having said that, Klube and Napier did bring it up as an issue back in the late 1970s, but they were basically told to shut up and go away. We're at the stage now where their research is being validated in a fairly major way. I think it's highly likely that we will find instances in the historical record that we can explain by intervention from the sky, not necessarily from the ground. And if that's the case, then it really does bring home to everybody the fact that what happens in the sky isn't separate from everyday life. It's actually an integral part in our development, our survival. It's an interesting field that's only just beginning to emerge now.
It's very interesting. I still can't seem to get David back.
You should be able to hear me okay there. You're doing a great job, so I'm just leaving it to you.
No, you can take it away from here, Dave. No worries.
Did we get that question there? What would happen if we spotted a bunch of the small but significant impacts with a number of hours to react? Is there a global UN response protocol?
No, not yet. If we did, if you're thinking about sort of Tunguska or Chelyabinsk size objects, probably the best thing to do is to hunker down and hope for the best.
Not really what we want to hear, is it? You think they would have?
You know, this is an issue where you have to ask the question, who's going to pay for it? And while it's not an expensive business, there is significant resistance from all nations, less for the United States, to actually invest more than a pittance into this game.
And has anyone estimated the cost of, well, I suppose you'd either have to have a very good survey system, and then you'd have to have a response system sitting on the ground ready to go. So that'd be a lot more expensive.
If your survey system is good enough, you don't need to have a response system fitting on the pad ready to go. Because with certainly reasonable sized asteroids, comets, you could reasonably expect to have months, years, even decades of notice, which gives you plenty of time to put something together, as long as you've got the plan, not necessarily the hardware, to put something together to deal with it. The smaller objects, you have to consider the cost-benefit analysis of either trying to stop the event happening or then dealing with the results of it happening. To take out something like the Chelyabinsk object would be, well, with current technology, impossible. With future technology, expensive. Would it be better to spend that money on clearing up afterwards? That is a question not for the science, but for the politics.
So I'll just check any more questions in our chat box. I don't see any, but while they're thinking about it, the Spaceguard Centre, so we can all go and visit it in Wales, is that correct? And how do we do it?
You go onto the website, spaceguardcentre.com. We run conducted tours of the observatory every day except Mondays and Tuesdays. And it's a case of you show up, you get an ear bashing for an hour and a half, and then you go away thinking that we're the best thing since sliced bread.
Fantastic. Well, look, we've had just over the hour, so we can always ask Jay questions online as well in the future. I'm sure we can contact you via the Spaceguard Centre.
Yeah, the website, as I say, you can always contact us through that.
Terrific, and we wish you the very best of luck with that telescope. 7.5 tons, what a monster project. When do you think, by the way, its first light might be?
Absolutely no idea. Mainly because jobs you think you can crack, this morning tend to last about 3 months. And the ones that you think are going to be really, really hard, you've done by lunchtime. And we're all on a very steep learning curve. We're learning skills that we never really wanted in the first place. I can tell you more about concrete than you would ever want to know.
And fiberglass.
Yeah, well, I mean, we're none of us are professional telescope builders, so yeah, it's a fascinating process, and my bunch of volunteers are frankly unbelievable. They are.
How many volunteers do you have?
Well, that varies week to week. Sometimes people can come, sometimes they can't. But we normally have anything from half a dozen to a dozen up each weekend. And wow. We just get on with it.
Yeah, even smaller group than I thought. Well, look, Jay, we might leave it there. Thanking you very much. I'm going to tell people about briefly what to see in the sky and the next talk on October the 10th. You're welcome to stay for that. If you've got to rush off and fix that telescope up, I fully understand.
Sadly, I have to rush off, but not for that reason. But no, let me just say thanks ever so much for the opportunity to speak. It's always a joy.
Oh no, thank you very much for agreeing to do so. It was a fascinating topic. Actually, you brought me right up to date. Love the statistics, so I'll probably watch that talk again. I see it's now available on our YouTube channel if anybody wants to follow me in that light. But thank you very much again, Jay. Hope it won't be 10 years again before our paths cross.
Well, hopefully not. Hopefully not.
I really have to make a trip.
We shall see. Anyway, I've got to go, but thanks ever so much, and best of luck.
Thank you very much, Jay. And
thanks a million, Jay.
We'll let Jay go there.
Well, no problem. All great. I'll see you anon.
I'll just briefly tell you about what's coming up. Don't forget, by the way, I'll tell you what's happening in the sky in just a second. But that RTE documentary, it's not often they spend our license fee on astronomy. So do support it. RTE Radio 1 Extra, Signs of Life. Every Thursday, 8 o'clock. Or watch the first episode now online. But what's happening in the sky? Well, this will cover till our next lecture on October the 10th. It's all in the magazine, by the way, which you can buy online, as I mentioned earlier. The planets on view. We've got a lovely view of Saturn and Jupiter now in evening skies. And even Mars is beginning to rise before midnight. You'll find more details of that in the magazine. So the morning planets have moved into evening skies. It's good to see. There's a big event, though, happening on Wednesday, just 2 nights' time. It's all detailed in the magazine. But the planet Uranus is going to pass behind the moon. Now, it won't be too easy to see because the moon is quite bright, Uranus is quite dim, but you'll get all the details and the times there around the 10 o'clock mark in the magazine. Don't miss that. Let's hope it's clear on Wednesday this week, 2 nights' time. The night after that, Thursday, the International Space Station comes back into evening skies, as I said. You'll see it every night until October the 4th. That's always a fascinating sight to see. It can outshine even Jupiter when it's making one of its high passes. And then if you look ahead, that same night, a bit later on, the Pleiades star cluster is actually quite close to the moon, about 3 degrees, so half a binocular field of view. So the moon and the Pleiades will be in the same field of view. That's Thursday night. There's a map diagram of that in the magazine as well. And then on the Friday night, so it's all happening this week, Mars is very close to the moon, about 2.5 degrees. That's about 5 moon widths. So well within the same binocular field of view. So it'll look really spectacular to the naked eye and even more spectacular in your binoculars. We were hoping to see Jupiter, was it last night or the night before? Last night, very close to the moon. I didn't see it, too many clouds around. It's often the way here. So hopefully we'll get to see Mars. It's now quite bright. It's into a negative magnitude. So as bright as the very brightest stars in the sky at this time of year. So definitely watch out for that. And then later this month, the planet Jupiter is actually at opposition, which means closest, brightest, nearly magnitude -3. And it's going to line up with the moon again 2 days before our next lecture on October the 8th. That details that will be in your October magazine, which we're just sending to the printers tomorrow, in fact. So hopefully you'll have at the end of next week, early next week, in your letterboxes. And that's going to be one of the most spectacular sights to see in October. Our next lecture is on October 10th, and 15 days after that is that partial eclipse of the sun, which will also be covered in the October magazine. So if you're a member already, wait for that to appear in the post. And if you're not, do sign up, as I said, at astronomy.ie. Now, if there's any Northern Lights forecast, we'll tell you all about those in our social media, which is where we'll also post our International Space Station predictions, and they're all free. If you follow us on Twitter, Facebook, Instagram, and even TikTok. So that's what's happening. Let me tell you about what's happening in the future. That's what's happening in the sky, sorry. Let me tell you what's happening on the ground. The evening classes, October 25th, same day as the eclipse of the sun. So that's easy to remember. At the radio show every Thursday night. And the members' email will be sent out every Wednesday. And that'll take us nicely up to our next lecture on October the 10th, 7 o'clock, online again. This time the title is Death from Space. It's actually an overview of cataclysmic events, not just asteroid impacts, but also gamma ray bursts and other things that could threaten humanity. It's going to be given by the famous author and astronomy communicator, Stephen Tonkin. Some of you may have read his books. And he promises a light-hearted but scientific tour of all these threats from space. That's October 10th. I don't think we've put up the Eventbrite page for that yet, but it should be up by tomorrow. So if you are on our mailing list, you're going to get a notice of that. You've got till October the 10th anyway to book your tickets for that as well. So that's everything that's I've got to say for the meeting this evening. Unless any of our volunteers listening in remind me of any announcements I might have missed. No, good. So we can call it a night there anyway, and thank Jay Tate from the Spaceguard Centre for a brilliant talk. And hopefully we'll see you all again on October the 10th, streaming away with our next talk by Stephen Tonkin. So thank you very much for tuning in. Hope you enjoyed the event. Okay, I'll stop the recording there. So we can all go home now. Nicole, Tom, you're all happy with that?
Yeah, I'll go, David.
Brilliant. Well, if anybody has any questions, just email us admin@astronomy.ie. We'll do our best to help you during office hours. And look at the comments here. Nothing else that I've missed. Oh, we did miss one question, but we'll have to ask Jay that directly himself. So good night, everybody, and we'll call and Tom. We'll talk to you tomorrow.
Good night.
All right. Night.
Thanks very much. Should I end the meeting, or do you want to do it, Nicole?
Sorry, I thought my mic was still on. Yeah, I can do it now.
Yeah, you end the whole meeting. I've only got a leave meeting on this one for some reason.